Hello, I'm going to talk about phonons. What I'm going to do is I'm going to have as the aim of this session to derive an expression for the heat capacity of a solid. Now we have already seen how the electrons, the conduction electrons in a metal can contribute to heat capacity. Now, the other contribution to heat capacity in a solid is the vibration of the atoms, and it is this contribution that I shall talk about. So, in a solid, we can imagine that there are many atoms that are packed closely together, and if you imagine moving one of the atoms, that atom will cause its neighboring atom to move, and in turn that would push the atom next to it. So if you disturb a single atom, that will cause a whole wave that goes through the solid. Now, there are mathematics of wave equations that are used to describe this motion and to derive formulas for the waves. Now, but for our purpose, all we need is to make use of is to assume that these are atoms that have small displacements and can be described by a formula like that, just a sine function. So we have waves going through a solid. Now typically in a solid, the thermal motion, the vibration of the atoms due to thermal energy is random. But we know from Fourier analysis that we can describe any functions using a sum of sine functions in the sense of a Fourier series or Fourier transform. So we are going to start by looking at one such frequency component of the motion, which therefore means that we'll look at a waveform. So if we imagine a wave-like disturbance traveling through a solid, then like in the case for the electrons or particles in an ideal gas, we can think about boundary conditions. Now in this case, we are going to choose as the boundary condition the simple case where the atoms are fixed at the two ends or two sides of a solid. So this could be my solid, and it could be this could be just part of a cube, and let's say the length of the cube is A. So length side A, and suppose that that's my origin here, that's my x-axis, so that's x equal to 0 and that's x equals to A. So once I've chosen this condition, then it is very much like what we've seen for the ideal gas, for the particle in a box. So where we treated the wave function and derived the quantization condition. So in the same way, because this wave-like disturbance through the solid has the two ends of the wave fixed at the two walls, we also have the boundary condition. Right. So when x is 0, the disturbance should be 0. I've chosen it to be a sine function, so that's fine. When x is A, that disturbance, this displacement of the atom at the wall should be 0 as well. So when x is A, that's 0. And this means that Ka must take the form of a whole number times pi. And then we have our quantization condition, which is exactly the same as what we've seen for electrons and for ideal gas. And because this is in the x direction, we put a subscript x there. And likewise, we have the corresponding conditions for the y and the z direction. Okay. Now, right, let me just stop for digress for a few seconds to clarify, to make sure that we know where we are heading. So the purpose of this is eventually to calculate the heat capacity, and to find the heat capacity, we know that we can do that if we can find the total energy. And to find the total energy, we would need the energy of the energy levels, and we need to know the number of particles at each level. So just like for electrons and the ideal gas, and which is why we are talking about density, we are talking about the quantization condition here, because the quantization condition, since it's the same as, it looks exactly the same as that of an ideal gas, it means that I can make use of the same the density of states formula for the ideal gas to tell us the number of states we can find at a given energy interval. Alright, so that's what this quantization condition will lead on to. Following the same argument as the ideal gas, we would therefore arrive at a density of states, the same density of states, gk v k squared over 2 pi squared, which is what we have seen for the ideal gas. So this tells us the number of possible k states that we can have. Right. Now, but in the case of phonons, there is a complication. The complication here is this. For a particular quantization condition, meaning a particular wave, let me clarify that. A particular wavelength, alright, the k here, or the kx here, essentially specifies the wavelength in a certain direction, because k is equal to 2 pi over lambda. Alright, it specifies the wavelength. So for a particular wavelength of the wave, in this wave in a solid, there are actually 3 possible ways that the wave can take place. Alright, it can vibrate in a direction which is perpendicular to the direction of travel. Alright, and we know that that's called polarization. So it can have a polarization in 2 transverse directions, and it can have a longitudinal polarization. That means instead of the wave looking like that, it can actually oscillate longitudinally, like in a sound wave. So there are actually 3 possible ways that the wave can happen. In other words, there are 3 polarizations for each possible set of quantization condition. So this means that when this is the same as saying that for each of the states that we expect in an ideal gas, that means each of the kx, ky, kz, there would be 3 polarizations. Now, as far as this system is concerned, each polarization is just another state. And that means that the density of states has to be multiplied by 3 for the 3 polarization. So this then is the correct density of states. So we have made use of the ideal gas density of states and multiplied it by 3, and that gives us the density of states for phonons. Right. Now, the next thing that we'll look at is the we need to look at the energy levels, and yes, but before that, I need to say a bit more about the density of states. If you recall from ideal gas and electrons, that we, in order to do the calculations for total energy after this, we transformed the density of states from the variable K to the variable E for energy. Now in this case, the more common way to do it is to transform this to the variable of frequency. Now the reason is, for phonons and as well as for photons later on, the relation between K, the wave vector, and energy is different from the relation for particles. In the case of photons and phonons, the relation between the wave and the energy is given by energy is equal to hf times constant time frequency, or h bar times omega, the angular frequency. So that's different if you remember from electrons in solid. We have a different formula that came from Schrödinger's equation for the kinetic energy. So in this case, it's given by this formula here, and it is often convenient, and this is also the way that it is often done, to express the density of states in terms of the variable of omega, the angular frequency, rather than in the variable of energy. So let's make the transform now, because that's what we're going to have to use later on. So we want to make the transform from Gk to G of omega. And if you recall, we need to treat the density of states function as a distribution function, which means that we can't do direct substitution of omega in terms of k. We have to consider the number of states in a certain energy, a certain k interval dk, and the number of states in interval d omega, and say that, right, because the interval dk corresponds to interval d omega, so therefore number of states must be equal. So we need to make use of this transformation equation, and we then need to find, we need a relation between omega and k. Now in this wave traveling through a solid object, it is actually the sound wave that travels through the solid. So that means that the relation is omega over k is equal to v. Now that's little v there is the speed of sound in the solid. Now I'm going to, we have another v, which is this one, is the big V. So that lends itself to confusion. So that's a big V. Right, for now, let me put little lines on top of the big V to show that it's a capital letter. So I have this little v there, which is the speed of sound in the solid, of course, not in the air. That's the relation, and I can now make the transformation. So G omega is equal to Gk dk over d omega. And I can differentiate that. Let's see. I know that k is equal to, if I rearrange, omega over v, dk over d omega is 1 over v. So therefore that's 1 over v. And gk we know to be that 3 big V k squared over 2 pi squared times that, which is 1 over v. And finally we can now make the substitution for k in terms of omega. Right, so k is omega over v. That gives omega squared over v squared. And the v squared will multiply by the v there to give a v cubed. And that then is the density of states in the variable of angular frequency. So let's try and remember that, and we'll need to make use of this afterwards. So the next thing we need to do is to find the distribution of phonons. That means we need to find the number of particles in each state at a particular energy. Now we have done that for Boltzmann distribution for the particles in a solid with different energy levels. We have done that for the ideal gas. We've done that for electrons and solids, where we got the Fermi Dirac distribution. Now, if you recall, in the ideal gas, I've made the assumption that it is very unlikely for two particles to occupy the same state. In the case of the electrons, the statistics changed. We had to take into account that the Pauli's exclusion principle, that each state can have at most two particles, at most two spin states. Alright, so no more than one electron can occupy a spin state. Now in this case, we have yet another kind of statistics, because phonons are bosons. Now, so we can have any number of phonons occupy the same states. So no more exclusion principle here. So that means that we need to start by looking at the number of arrangements again and obtain a formula for that, and then maximize that using the Lagrange multiplier method. The steps are very, very similar to what we've done before. So let's go through it. So let me just write down where we are heading. We are going to obtain an expression for the Lagrange function. And the Lagrange function that we have seen has a log omega for number of arrangements plus terms to constrain the number of particles and the total energy. Now, in the case of phonons, actually, the number of photon particles does not have to be fixed, because phonons are packets of energies that appears because of the vibration in the solid. So if you heat up the solid, there will be more phonons. If you cool down the solid, there will be fewer phonons. So unlike the case for electrons and the ideal gas, where the number of particles, number of atoms, number of electrons have to be fixed. In this case, the number of phonons is actually not fixed. It depends on the temperature. So there is no longer a constraint on the number of phonons. And that means that we can cross that out. Now that makes a big difference to the final answer. And the good thing is, it also makes it simpler. Let me just sketch some energy levels. And suppose that we look at one particular interval of energy at around this energy EI. So I'll call this interval, let's say this interval has a width of dE. And in this interval would be some phonons. And I'll use the same convention as before. I'll say that there are GI states in this interval and there are Ni phonons. So within this interval, the number of arrangements I need to find. So if you recall, for say the case of the electrons, we had the restriction that we must not allow two electrons to come on the same state. But in this case, there's no such restriction. So what I can do is this. I have this little balls here that represent phonons, and I can think of the lines which represent the states. I can think of these lines as little rods. So again, I have the two types of objects, balls and rods. And it really doesn't matter how I arrange them. Alright, because it doesn't matter if I have lots of balls next to a ruler. So I'm free to arrange it anyhow I like, any of these GI objects and Ni objects I like, in a row or a column. So in this case, we can therefore make use of a formula for combination. The total number of objects would be Gi plus Ni, but the total number of balls and rods is Gi plus Ni. So factorial. And then because there are Gi identical rods, I must divide by Gi. There are Ni identical balls, so I divide by Ni. And there we have our number of arrangements within this interval of energy. Now in order to do it for the whole range of energy, we need to multiply together the arrangements for all the intervals. So we multiply the whole lot, like we did for electrons and gases. And then after that, we will take the log. So the steps are familiar. If I multiply a lot of these together and take the log, I will get log omega 1 plus log omega 2 and so on. Alright? And in anticipation of what we are going to do with the Lagrange function, we want to differentiate that with respect to Ni. Right? The purpose is to find the maximum Lagrange function with respect to the variables of Ni. Ni is the number of particles that we want to find. Differentiate log omega by Ni. So omega I is a function of Ni. So omega 1 is a function of N1. And if I differentiate with that with respect to Ni, that would be 0. So all the terms would be 0 except log omega I that has the same variable as Ni. So I would differentiate that. Now to differentiate that, we use Stirling's approximation. Now Stirling's approximation, if you recall, would would give, when you take the log of this, let me just write this part out, this would look like log of easier if I write this out first. So log of omega I would be log of gi plus ni factorial minus log of gi factorial minus log of ni factorial. Alright, so just that. And Stirling's approximation then gives, that would be approximately gi plus ni bracket log gi plus ni minus bracket gi plus ni. Alright, and I would have minus of log of gi factorial, but that's going to differentiate to 0, so I'm just going to leave it as log gi factorial. Alright, and I would write minus log ni factorial as using Stirling's approximation as ni log ni minus ni. So that's what this log omega I looks like. And we have to differentiate that. So let's try that. So when I differentiate log omega by log ni, this should be partial d's. So I need to differentiate this. Alright, so that differentiates to 0. And these terms look exactly the same as what we did for electrons. So if I differentiate this would give just 1, and I have log gi plus ni. Alright, and when I differentiate the log, the result would multiply by this to give a 1. When I differentiate that will give a 1. So the other parts of this differentiation cancels. Now that's a constant, so it differentiates to 0. And that we have done a few times already. So I'm just going to write down the answer. It will be log of ni. So it becomes a lot simpler than the first expression. So this is what it looks like. And the next thing we also need to differentiate would be the u. Now remember that u is n1, e1 plus n2, e2 and so on. So if you differentiate u with respect to ni, you will just get ei. So we have what we need now. So dl by d and I is equal to that, differentiating that gives this log gi plus ni minus log ni. Differentiating u gives ei plus lambda 2 ei. That's that. And to maximize this, we equate this to 0. And now we can solve for ni. So let me bring the two together. Log gi plus ni over 9 E2 what's that? Okay, bring that over. Invert the log. Okay, rearrange. I'm going to jump the rest of the steps. We will have to bring the Ni over there to become minus Ni. Factor out the Ni to give E minus argument minus 1 and bring the whole lot over to the left. And that gives Gi over E minus lambda to EI minus 1. So that's what it looks like. That's that. So finally, we have our solution. And we already know what lambda 2 is from the previous two distributions. So we can write this now as, so I'm going to just write this out as Ni is equal to Gi, write this to the side, Gi times 1 over exp ei over kbt plus minus 1. Right, that's what it looks like. You can see that, right? Yes, so that's that. So now let's put it in a form that is easier to integrate with. Since Ni is the number of particles in the energy interval dE, let's divide that by dE, and Gi number of states divided by dE, and this gives the number of density Ne, density of states Ge, and then the E to the E over kBT minus 1. Right. So we have now a form that has some resemblance to the Fermi-Dirac distribution, but it doesn't have the mu, the chemical potential. And instead of a plus sign for the Fermi-Dirac, we have a minus sign here. So these are two important differences. The fact that it doesn't have a mu is because, if you recall, the chemical potential term in Fermi-Dirac, that is directly related to the number of particles, which is fixed. And the number of particles fixes the mu. So because in this case, the number of phonons is not fixed, so we don't have that mu, which came from the other Lagrange multiplier. So it's just the E there, and if you remember the expression Fe, which I've used before, that corresponds to this part, this factor here, 1 over E to the E over K Bt minus 1. Right? And that gives us a number of particles, in this case a number of phonons at a particular energy state. And remember that in this case particular energy states means a particular set of Kx, Ky, Kz and a particular polarization, either one of the two transverse or the longitudinal. So that's that. So we now have an expression for the number of particles at each level. Okay, and we are finally ready to write down an expression for the total energy. So to write down the total energy, we start with, let's see, we can think in terms of the original formula, N1E1 plus dot dot dot, NIEI dot dot dot, okay. And in terms of this, we would have, say, if each of these terms there represents a little interval of energy. So in order to get this, then in the small interval there, we need to first find the number of states. Okay, multiply by the density of states, and then we need to find the number of particles in this interval. So I would multiply the number of particles in one state by the number of states. So that actually gives me number of particles. And then I would need to multiply by the energy of each particle. And then I need to sum or integrate over all energies. And in the case of phonons, as I've mentioned, it is conventional to work in the units of angular frequency rather than energy. And energy is related to angular frequency by h bar omega for phonons. So this is the energy of one phonon at that frequency. So in the energy frequency, it would look like this. So instead of having it in terms of energy, we want to have this in terms of frequency, right? So instead of writing it in this form, we would replace this by F omega instead, and we would replace the E there by h bar omega. So it looks like this. Right. E to the power of h bar omega. Now we have to be a bit careful here. Previously, I've written F epsilon as equal to being that expression there. So now all I've done is I've replaced the E by omega rather than using the h bar omega. Alright, rather than substituting h bar omega in here, I've actually dropped the h bar omega. So in this case, the f here is actually a different function. So I'm using the function a bit loosely here. Alright, and the way to understand this is that if we would just look at that function, that variable, and if that's omega, we would understand f to mean the number of particles in a state that has angular frequency omega. So that means that this, I'm assuming that those two are equal in a sort of descriptive sense rather than a mathematical sense. Alright, so I would call that F omega. And G omega we already found earlier on. We'll plug that in afterwards. And E here would be H bar omega. That should be omega. Now we have already sorted out the mathematical issues with the density of states. Alright, we've already seen that because it's a distribution function, the variable transforms by setting an expression like that to an expression like that. So we understand this bit. Alright, it is the going from this bit to this bit that was a bit vague just now, but I explained that. And E here is the H bar omega for phonon. So this is the formula. And we are sort of alright so far, except for one thing. And that thing is about the upper limit, the integrating to infinity. Now this is a problem. Let's see what the problem is. If you recall the picture I drew of the displaced atoms that propagate like a wave, it looks like a wave in the sense that the particles are arranged along what seems to be a sine curve. And that's fine. But the thing is, this wave is a wave in the sense that it is defined by this arrangement of the atoms. It is as if the wave is made by drawing the curve using the atoms, or using the atoms like little pixels in a picture. Now there is a problem here if you start thinking of very high frequencies. At very high frequencies, the wavelengths get shorter and shorter. Think about what happens if the wavelength gets shorter than the distance between the two atoms. Can you imagine having a wave between two atoms? If, as I said, we effectively drew the wave or created the wave by putting particles into the shape of a wave, then in this empty spacing between two atoms, there is nothing to draw a wave with. And that just means that it is not possible to have wavelengths that are shorter than the spacing between two atoms. In fact, it is not possible to have wavelengths that is shorter than the distance, than twice the distance, if you think about it. Because with just two atoms, you can't draw our wavelength either. So anyway, the point here is that there is a limit to how high a frequency you can get in a solid. These waves, due to the displacement of the atom, there is an upper limit to the frequency. So it cannot go to infinity, actually. Now, we will call this upper limit omega d. Now, this upper limit of the frequency has a name. It is called the Debye frequency. Right? And we are going to have to look at how to obtain this Debye frequency afterwards. So let's take a break for now.